In this video we're going to talk about the simplest type of output stage, which is called a Class A amplifier. The phrase Class A amplifier is a very fancy way of referring to an emitter follower. It has a few extra implications, but not that many. We'll talk about them on a later slide. I've drawn two emitter followers here, one with a resistive bias and one with a current mirror bias. I've also chosen to power this emitter follower with split rails, both a positive VCC and a negative VCC. The negative VCC rail is often named VEE, but I've just put its voltage value here to simplify our notation. The split rails let us pick the DC bias of our emitter follower, Vin, such that our large signal or DC value for Vout is 0, which means that no power is dissipated in RL when the signal indicated by little Vin is 0. You'll note that I said little Vin rather than small signal Vin here, and that's because little Vin isn't necessarily a small signal. Since we're trying to drive very high power into the load, little Vin could swing all the way from rail to rail. But I chose to use small signal notation to indicate that little Vn changes while this large signal Vn is a constant. Emitter followers have a small Rout value, so we might have an instinct that they'll be good power amplifiers based on the max power transfer theorem. We need to do some large signal analysis to confirm that suspicion. First, we note that Vout is just our total signal Vin minus VBE on. That means the amplitude of the output voltage waveform on Vout is the same as the one on Vin. However, the current driven into the output is going to be about beta times higher than the current that's driven into the base. That means we get the same voltage at a much higher current on our load resistance, which means that we have increased the power delivered to the load. Finally, it's worth noting that the reason our initial suspicion wasn't sufficient proof that this is a good power amplifier is because Rout changes over the input cycle. If we imagine Vin as a sinusoid, when Vin is at its peak, we'll be running a lot of current in Vout, which means that Rout will be very small because GM will be very large. But at Vin's trough, the current in our device will be smaller and GM will be larger. So, our small signal parameters vary over a single operation cycle of this amplifier, but it's still kind of useful to estimate them sometimes at peak values. The resistively biased emitter follower is relatively unpopular because it's tough to analyze, and as a result, tough to design. You'll see something that looks like this circuit in a lot of places, notably in voltage regulators, where the value of Vout is controlled by feedback. Voltage regulators, by the way, are also cute because they just replace RE with an open circuit and use RL as the DC path to ground for our power device. I think that's clever. However, if we look at a detailed calculation of the output voltage, where VBE on has been replaced by phi th times IC over IS, the natural log of IC over S, we realize this is going to be a brutal equation to solve. Notably, figuring out IC is a transcendental problem, and that's before considering that we have sort of a linear Vout here and then a log probably of some function of Vout here. The active load sidesteps that problem by pinning the total current that flows through the device here and RL. We know that the current in RL plus the current in this device has to be equal to IB, which is going to be the current flowing in this device down here. Finding Vout is still a transcendental equation under that condition, but if Vout over RL is small, then this equation becomes pretty easy to solve. And if V out over RL gets close to IB, we know that our analysis will break down. So we can start seeing what will happen at some kind of extremes of V out and RL values pretty easily using this equation, where we can't with this one. One easy way to start understanding the large signal behavior of this amplifier is drawing the voltage transfer characteristic, or VTC, which you'll recall is a plot of large signal V in versus large signal V out. I've put the axes over on the right to start doing that. I've also included the equation describing V out from our last slide for reference. We can start by noticing that the VTC will basically be a straight line for much of the curve. In this region, IB is much bigger than V out over RL, so the logarithmic argument here is going to be about constant, and that means the slope of this line is going to be about 1. This line has a value of 0 when V in is equal to VB on, and that's because of the diode drop across Q1 here. So when V in is equal to VB on, then V out is equal to 0, and there's no current dissipated in RL. So picking V in equal to VB on is a common choice, because then when your input signal isn't moving around, you have no DC power. In the case that RL is big, this V out over RL term never gets close to IB. And so that means our output can swing all the way up until Q1 becomes saturated at VCC minus VCE sat, or all the way down until Q2 becomes saturated at minus VCC plus VCE sat. Hitting this Q1 failure mode is unusual because it requires V in to go above VCC. The input is VBE on above the output, so at the maximum output value, this would be VCC minus VCE sat, and this would be VCC minus VCE sat plus VBE on. And because VBE on is bigger than VCE sat, that's above VCC. So usually we'll be limited in our swing in this amplifier by our driver, which always confines us to this linear region. However, if RL is not very large, then there's another possible failure mode for this amplifier. If the current in Q1 goes to 0, it's cut off, and then Q1 won't convey any additional changes to the circuit as V in varies, right? If it's cut off, it's not like it can start pulling current back up it. So that happens when there's no more current running in Q1, which means that the IB of current that's running in Q2 has to all be running in RL. And if we have IB running in R backwards through RL like that, then the voltage V out will be at minus IB RL. So you can sort of think of the operation of this power amplifier as Q1 when it's on stealing current away from RL in order to increase the value of V out. But once Q1 has stopped stealing any current, we've reached the limits of how low the amplifier can go. This appears in this equation, by the way, or this behavior appears in this equation, because if V out over RL becomes a negative value and equal to IB, then we'll be taking the log of 0, which means VBE blows up to an increasingly large value, showing that our sort of Vn minus VBE will stay the same as Vn increases. Alright, so that means there are two possible conditions that can set the minimum output voltage of this amplifier. And which one dominates depends on the values of IB and RL, which you can anticipate as a designer. One desirable condition is to have these two lines land right on top of each other, so that our two failure points occur at the same voltage and we're not spending any extra bias current on top of what we need to achieve the maximum swing. So that occurs when minus IBRL equals minus VCC plus VCE sat, or canceling out the minus signs under this condition. It's common to use the efficiency as the main figure of merit for power amplifiers. So I want to show you one or two efficiency analyses in these videos to familiarize you with how it's calculated. However, we're not going to do a lot of efficiency analysis on our own in lab, so enjoy the show and try to remember the rough outlines of this process, but the main thing to take away is the result at the end of the page. When you analyze efficiency, you usually do it in the most favorable condition for the amplifier. For this power amplifier, the most favorable condition is when the voltage swing is at its maximum value. That's because the IB current is always flowing, whether you're putting it in the load resistance or not. So we want to drive a big output voltage to ensure that all the IB current gets used up in RL, making a big voltage swing. For the same reason, we want to make sure that IB is as small as possible, as long as it doesn't interfere with us achieving our maximum voltage swing. That gives rise to these test conditions. We're setting IB to achieve the maximum swing, and that was a calculation we did on the last page. We're letting large signal Vin equal 0.7 volts so that we have no DC dissipation in RL when our little signal isn't moving. And we set the amplitude of our little signal to the maximum value of our swing and our transfer characteristic, VCC minus VCE sat. And then we say it's a sinusoid. Okay, so the power pulled from the supply is equal to the power that comes out of VCC plus the power that goes into negative VCC. The power into negative VCC is pretty easy. We always have IB flowing into Q2, so it's minus VCC times minus IB, because the bias current is flowing into it, not out of it. The power flowing out of VCC here is a little trickier. Our voltage is always VCC, so that's easy, but the current flowing out of it is equal to the collector current of Q1. And that, it turns out, is given by our bias current times 1 plus sine omega t. We can figure this out because the collector current that flows when our small little Vin signal is equal to 0 has to just be IB. Vout has to be 0, so all of the bias current from Q2 has to flow into Q1. That explains this 1. And then we know we're going to see a sinusoidal variation in our current as Vout moves, because Vout is linear with RL. And we know that the peak value of that sinusoidal variation is going to be IB, because the highest voltage here will be VCC minus VCE sat, and VCC minus VCE sat over RL is our IB value. I've chosen to, instead of writing VCC minus VCE sat over RL, write IB for reasons that'll become clearer as we go through the analysis. So time averaging this, we find that our power pulled from the supply is 2 times VCC times IB. And that makes sense because on average IB is flowing from plus VCC to minus VCC. So 2 VCC is the change in voltage, IB is the current. The power dissipated in our load is the output voltage times the current in the load. So our output voltage is given by Vin minus 0.7, so just the little Vin signal. And our current in the load is linearly related to that. It's just our output signal divided by RL. And again, I've decided to write VCC minus VCE sat over RL as IB here, rather than as the full notation. Time averaging this, these two factors of sine turn into a factor of a half. Finally, we calculate the efficiency by dividing the power in the load by the power in the source. The factors of IB cancel out, which is why we kept writing them earlier. And we then simplify our resulting expression to find 1/4 times 1 minus VCE sat over 2 VCC. And this is usually a pretty small number. So our efficiency is about 25% overall. That's quite bad. And this is also our maximum efficiency. This gets worse as we scale off from our maximum swing. As we back off from our maximum swing. And the main issue that causes both our low efficiency and our poor back-off properties is because we're always dissipating IB from our supplies to keep Q1 and forward active. So we might wonder if we can get away with not running current in Q1 all the time. And that line of thinking leads us to some other very common amplifier topologies called Class B and Class C amplifiers. This circuit on the left can equally represent Class A, a Class B, or a Class C amplifier. The only difference between them is the value of V in and the amplitude of little v in. A more technical way to think about whether amplifiers are Class A, Class B, or Class C is called the conduction angle, which I've chosen to note with theta C here. And this is actually how Class A, Class B, and Class C amplifiers are defined. The conduction angle refers to the fraction of the input period during which current is running in our output device in Q1. And you can see that for a Class A amplifier, the conduction angle is 2 pi, or put another way, we always have some current running in Q1. That's illustrated in this plot of the collector current of Q1 against omega t. Now, we're using omega t here so that we can talk about fractions of a period that Q1 is conducting without having to talk about what specific frequency we're at. So using this abstraction of plotting against omega t is really handy, and it's where the idea of conduction angle comes from. So because we always have some current running in our collector, our conduction angle is 2 pi. Class B amplifiers are defined by having a conduction angle that's about pi, so it conducts for this half cycle and not for this half cycle. And Class C amplifiers are defined by having a conduction angle significantly less than pi, so we get this narrow little spike. However, if we were using the same input as Class B, we'd expect this spike to be pretty short, like just a little bump there, because you have to put a pretty negative V in to make a Class C amplifier work. So Class C amplifiers are usually driven very hard by a large little V in, which I've indicated by the height of this spike here. You might look at the Class B and Class C amplifier outputs and say these don't look anything like sine waves. How could we possibly get a good representation of V in on V out using them? And you'd be right. However, there are circuit tricks we can do to improve the performance of Class B and Class C amplifiers. These include something called a push-pull topology, or by adding output filters, which are things we'll talk about in the next videos. So in summary, emitter followers are power amplifiers with maximum output voltage of VCC minus VCE sat, and a minimum output voltage that is given by one of two conditions, either minus VCC plus VCE sat, or minus IBRL, where all of our bias current is steered into our load, and as a result our conducting device is cut off. When emitter followers are operated as Class A amplifiers, so they have a conduction angle of 2 pi, they achieve 25% efficiency. Backoff degrades the efficiency of Class A amplifiers because our bias current is running all the time. And Class B and Class C amplifiers are the same topology as Class A amplifiers, but they have less conduction angle.